But whether you've got, how much time you've got to do it's another story. Plus you need to be on top of linked lists to do it, okay? All right. We're back on? Okay, all right, everyone. We're going to start back now. Hi, everybody. Sorry we dropped out for a while. Just talking about assignment 2. We'll be working with a larger problem and a large code base. So you'll be given quite a bit of code that you're going to have to add code to. And that's similar to things you get, everyone be quiet. That's similar to what you get in the real world. You'll be working in teams. You'll be working with existing code. You've got to make sure that your code's written in a way that interacts properly with the rest of it. You'll be working with multiple C files. So you'll be given code in one C file and a .h file. You'll be writing code in another .c file. I don't know if you heard this before. You have to use the linked lists. You can't get rid of all the linked lists in the program and do it all with arrays. You'll get 0. There'll be strings in there. You've got to make sure you're using your heap properly, freeing things. There'll be style. And an important thing, if you're a COMP1511 student, you only have to do stages 1 and 2 of the assignment. Okay? COMP1511 students just do stages 1 and 2. COMP1511 do the whole assignment, like just the extra stages. Okay. All right. So the live stream will be Monday, 4:30. There's a YouTube link up on the assignment spec when it comes up. The recording will be available. And the assignment's due Friday, week 10 at 5 o'clock. As you might have learnt from last time, don't leave it to the last minute to get started. So then you've got time to go to help sessions, time to ask questions on the forums, get answers, time to let your brain have a break from doing it. If you try and do it in one sitting, it's very stressful, right? I don't know if anybody sat there for way too many hours at once doing assignment 1. It gets quite stressful. All right. All right, so that's coming out, but today we've got a really important lecture because we're going to introduce linked lists. But malloc is a crucial thing to understand, so we're going to do a bit of a recap of malloc first. Okay? Lecture code's up as usual. All right, so is everyone clear? Shh, everyone be quiet, because we have had complaints that people are too noisy, people can't hear in the hall and also at home. Some of the complaints were also in the week where there were alarms. That wasn't anything we could avoid, but we can kind of keep it quiet in here. So is everyone happy with the difference between the stack and the heap? Well, not happy. Do people get the concept? So when we compile our code, it's just a file sitting there. Once we run it, it's executing and it gets a chunk of memory, or what you might think of as RAM or call RAM, that it uses. And the code that we've compiled into noughts and ones, that's machine code, that's loaded into RAM because all the instructions are there in RAM, and that's in the code section. So that's one section. And there's another section for global and static variables that we don't purposely use in this course at all, really. Then the main two parts that we're worried about are the stack and the heap. Now the stack just does its own thing. The stack is controlled by the system as we're creating local variables, or as our functions run. They'll get a frame on the stack where they can store their local variables and other information as well. And that information is going to be put on and taken off the stack automatically. I mean, we get to decide what values we want to store in there, but the space is being allocated and deallocated for us automatically. With the heap, that's our space to use as we like. That's a chunk of memory where we get to say, give me some of this memory, and then later say, yep, I'm done with this memory. So we've got full control over that heap. Okay, so the command that we use to ask for memory on the heap is called malloc. And when you use malloc, you've got to remember, which I foolishly forgot the other day, that it's in bytes. So if I want to ask for enough space for 10 integers, for example, which is what we're doing here, I have to say 10 multiplied by the size of an int. I can't just say 10. Otherwise, you'll get errors. Go back to the last lecture and see. So you've got to say 10 times the size. And on our system, that will give us 40 bytes. So we're asking, can you give me 40 bytes on the heap? Now, the heap has to be able to have 40 bytes all in one contiguous block that it can give you. Hopefully, our system has 40 bytes. If it doesn't, just say you've done lots of mallocs already, there might not be a chunk of memory big enough for what you want. It will return null. If it can give you that memory, well, it gives you the address of it, so you know where it is. And what can you store addresses in? Pointer variables. So we get back an address and we store it in this pointer variable, and we're going to be using it to store integers. That's why we've made it an integer pointer. Now, if I've got a chunk of memory and I'm just storing 10 integers in it, that's kind of pretty much what? What would you call that data structure? Yeah, it's basically an array. We've made our own array. We've asked for enough memory and we've made our own array. It's got different syntax to the arrays we've made before, which are static arrays and are on the heap. We call this a dynamic array, but we can still use it with our array square brackets and indexes. All right. So typically we do a malloc, we get a chunk of memory, we do whatever we want with that memory, and then at the end we free it when we're done. Yeah, we've got a question?
You were calling the malloc dynamic, and I'm a bit confused when you have the 10 in there for the amount of bytes you want to assign to it. If it's dynamic and you don't necessarily know how much you want to assign, how do you pick a number there?
Okay, so the question is, I've hard-coded 10. That doesn't seem very dynamic. That's true. But what you could do is, instead of having a hard-coded 10, we could use a variable there that we've tried to work out either from the user telling us something or a calculation how much memory we might need. Then, what can we do if we run out of space if we've used malloc that we can't do if we just use static arrays? Does anyone remember? You can do a realloc later. You can say, actually, I made this size 10, I want it to be size 20, which you can't do with the other array notation. The other thing about this is I can return this from a function. I can create this and return it from a function because it's going to live on the heap and it will still exist when the function finishes. That's not necessarily answering your question, but does that make sense? Yeah. Again, we're never going to be able to be mind readers and predict exactly how much memory we're going to have in our array, unfortunately. And that's exactly why we'll be looking at linked lists today. So anyway, that's a very good question. So when we're done with it, we free it. If we don't free it, when we run DCC with this extra flag, DCC will complain and tell us you forgot to free something. And in our small programs, forgetting to free something mightn't really break it. It might not have any repercussions to you when you run it. But in long-standing code, bigger programs, you'll eventually run out of memory. So we want to make sure you always free all your memory. And in assignment 2, you'll have to free memory, and we'll be doing some auto tests where we run this leak check to see if you have. All right, so what we're going to do now is just an example. We're going to return a pointer to a struct from a function. So we're going to, I've got this struct coordinate. It's just a simple one with an x and y. My function's going to get the x and y value, and it is going to return a pointer to one of these structs. Then we're going to write a function that can print one of these structs if we've got a pointer to it. Then we're going to write a main function to use these things. Okay. All right, so create coordinate. Now the first thing you might be tempted to do is do something like this. and basically, you know, take what you're doing here is you're creating, that's creating a chunk of memory, and you're saying, let's go and put this value you've passed in into the X field. Let's put this value into the Y field. And then you might be tempted to return the address of that. Now, how would I return the address of that? How do I get the address of something? Yeah, so I'd go like this. And that matches, all the types match up. I've got a struct, I'm returning the address of it. Does anyone remember what's wrong with this?
You can't return a pointer.
We can return a pointer.
The memory is in the stack.
Yeah, this memory, exactly, that's right. So you can get a chocolate now on the break. But the memory's in the stack. What happens when this function finishes? What happens to local variables which are on the stack when this function finishes? Yeah, that part of memory on the stack, you know, the function's finished, that gets popped off. That frame gets popped off so it can be used for something else now that the function's not running. So actually, that sort of doesn't exist anymore. So you've given back an address to something that doesn't exist. So if you tried to compile that, let's just do it. DCC will complain. And if you actually tried to run it, oh, it doesn't. Oh, I haven't saved it. So there's nothing to complain about yet. If you tried to actually run it, it'd either crash or give you weird output or something like that. So it's saying, no, you can't return the address of something that's on the stack, which all local variables are. So what do we do if we don't want something to be on the stack? Yeah, malloc it. So when I malloc it, I'm going to ask, I don't want to try and calculate this myself, how big it's going to be. I need to find out how big it is on the system. I want enough memory for a struct coordinate, right? And it's going to pass back the address. I have to store an address in a pointer variable. So right now, I have a variable called mycoord. I'll choose a different color. And it's got the address of some chunk of memory that's on the heap that's big enough to store a coordinate. That's assuming that malloc worked and we didn't get return null. I should check for that. But whatever this address is, you know, here goes another fake address. That's going to be stored in our pointer. We know where this chunk of memory is. Once I've got a pointer variable to a struct, how do I set the data inside it? Yeah, so usually we use dot to access the members of our struct. When we've got a pointer, we use arrow. Oh. So now I've gone and set these values inside to be whatever they, you know, the user passed in. Now I need to return, basically I want to return the address of this struct. How do I do that? Yeah, mycoord. So mycoord contains the address of that struct I want to return, and it's already a pointer. So I return that. So some people might get confused and try and put an ampersand there, but this is already a pointer. Okay, now because I've done that, when this function finishes, this variable will be, actually let's wait till I've written the main. So how do I use this in the main? I would say struct coordinate, I'm just going to call it C, equals create coordinate 10 minus 1, whatever. Now when I do that, Obviously, it's calling this function, which has done exactly what I just told you. But up here in the main, I've got a variable called C that's on the stack. Now, when this function down here finishes, it returns my coord. So it's returning this variable value, and we're storing it in our C variable, right? We're returning it and we're assigning it to this value. So now the C variable has the pointer to this struct. So now when this function finishes and all of its local variables on the stack disappear, we've been passed back a pointer to this struct which is on the heap and still exists. Yep?
Do we only use malloc when we need to create a chunk of memory for the pointer?
It's not about, so the question is, do we only write malloc when we want a chunk of memory for a pointer? What we actually want to do is, it's sort of the other way around. Whenever we want to do a malloc, we need to store the result in a pointer, but we want the malloc when we want to create something on the heap so it doesn't disappear when the function finishes, or with an array where we might want to not know in advance how big it is and make it a certain size based on what a user tells us or some calculation, or be able to reallocate later. So it's, yeah, if you want to make it inside a function and it still exists when that function lives, or you don't know how much memory you're going to need in advance.
We only use them when we don't want to remove it. So we only use them when we don't want to remove the memory.
Yeah, we only want to, we use it when we want to control how long we have that piece of memory for. The rest of the time, if we've got local variables, it's much easier to have stack variables that are taken care for us. But if we need more control over the lifetime of that memory, how much it is, that's when we step in and do our own mallocs. Okay, so that's that part. Now, when I print it, oh, I have to write print. Ugh. So again, here I've just been passed in a pointer, and I know that if I've got a pointer to a struct, I just use the arrow. So I'm printing, I don't know why this is called P. I think I'd called it point before, but I decided having point and pointer was confusing. So I just print it like that to make it look fancy. Not very fancy. I do that. So up here, when I'm calling this print coordinate function, print coordinate, again, what do I pass in here? Just C. I've already got a pointer. I'm not going to do ampersand. I've already got a pointer here. All right. Now, is there anything else we might need to do? So this, look, maybe I should just for my own sanity put a new line there. Anything else I should consider? Yeah, I heard somebody say free. So if I run it, and I'll just make this a little bit bigger. If I compile it with this flag, it's turning on the leak check, and it's going to tell me that on line 36, we did a malloc and we didn't do a free. Okay, and that's the first time, that's the first memory leak. Now there might be more. If we fixed it, there might be more. In this case, there can't be. It's a very short program, right? So when are we going to free this thing? Well, we don't want to free it until we've finished with it. So we'd free it here. This goes to whatever that address is, and it says, it gives it back to the system, and the system can use it again. We can't use it again after that. All right? So if I run it now, hey guys, there's some people that are really noisy over there. Do you mind just keeping it down? All right, cool. All right, now we've got no memory leaks. All right, the other thing is don't use this again. After you've freed it, oh, it's warning us. Yeah, you'll get runtime errors if you freeze something and then try and use it. All right, so that's malloc and free. Any questions before we move on to linked lists? Yep.
For the struct function, can't you just use the void function but make it so that the malloc changes, it is a pointer that changes the address that's in the index and int1. Kind of like the one below, but this time have a malloc that points to x and changes.
Okay, the question was, could we have a void function that changes the address of something? You could, but that would be a pointer to a pointer. So we don't want to go there. We can talk about it later. Yep, yep. All right, let's go to linked lists. All right, so just before we start, you don't even know what linked lists are, but they're basically a data structure. So it's a way of storing a collection of data. And we already know one data structure, and that's an array. So arrays are still great. We're still going to be using them. This is another option. So there's not one data structure that's good for every single occasion. Sometimes arrays will be the better choice. Sometimes linked lists will be the better choice. When you go and do COMP1511 or whatever, you will learn even more data structures. There's lots of different ones. So we're just doing 2 common ones in this course. So linked lists are suitable for sequential data. What does that mean? Well, you know, if you've got a playlist of songs where maybe you're going to press play and they're going to play one after the other, that's sort of sequential. Or an image gallery where you've got images and it's displaying them one after the other. Things like that, they're suited to that. Web browser history, or, you know, even just going back through websites. Let's think a little bit about arrays. We do know about arrays. So arrays, we know, store collections of data that are all the same type, and they do it in blocks of contiguous memory. So they're all bunched in together in one block. And they're great for sequential access, meaning it's very easy for us to loop through every single thing from beginning to end in order. They're also great for random access. I don't have to do a loop if I just want to jump to index 99. I just go there. I don't have to start looping through I till I get to 99. So it's good for random access. That's what that means. It's really easy to insert or delete items at the end. So sometimes we make an array that's really big and we just keep adding data to it. So if I knew the size of this was 5, like if I knew I had 5 elements in this list already, I'd know to insert the next one here at index 5. If I wanted to delete something at the end of this array, now I don't know if we've seen this kind of thing. That's easy too because it's here, right at the end, okay? And what I'd really do is just say, okay, the number of elements in my array was 1, 2, 3, 4, 5. Now it's 4. That's how we kind of delete things in arrays. Anyway. Now what it's bad at, or just messy or inefficient, is inserting or deleting in the middle. So imagine I wanted to insert some new item here, but I don't want to overwrite the 3. I want all this information to still be there. I just want to insert it between this data. Now, if I don't want to overwrite the 3, and I don't want to just move 3 to the end or something like that, I'd need to then move all of these over one spot. I'd need to go and have a whole loop moving everything along. And if I've got a lot of data and I'm doing this all the time, this becomes a bit inefficient. If I wanted to delete it, it would be the same thing because I can't just sort of have a hole in this array. So potentially if I wanted to get rid of this element, I'd have to move these back along. So I'm moving data, it's inefficient, but also if I had a pointer to one of these items, I've now moved it. That pointer wouldn't have the right address anymore. So there's that consideration too. Oh, I've just said that. And then there's the size of our arrays, which you just, what's your name, sorry? Yeah. Connor, that Connor brought up before. We never really know how big to make our arrays. Even if we want to use malloc, we might fill it up and we might have to realloc. If we didn't use malloc and a static array, well, we're just done. We can't add any more. But even if we realloc it, how much do we realloc it? Do we double it and waste space? Do we just keep adding one more chunk? You know, there's never any exact answer. So linked lists, what are the advantages? Well, linked lists by design are dynamic and they're designed to grow and shrink as needed. So they start off with taking up no memory at all, really, and then you want to store something, you do a malloc for that piece of data. You want to store something else, you do another malloc for that piece of data. So they're as big as they need to be. You delete something, you free that piece of data. They don't use contiguous memory. So we can put our data in all different locations around in RAM. So even if we don't have one huge massive chunk together, we could use smaller pieces of memory. And as we see, to insert or delete something, we're just changing pointer values. We don't have to move our data around to delete or add something. So they're the advantages. The disadvantages, and this can be a big one, is that it's not good for random access. So unlike an array, if you want to go to the 99th element, you will have to do a for loop and or a while loop and start at the beginning and go along one by one. There's also a little bit of extra overhead storing extra pointers, but you know, that's not usually a big deal. All right. So this picture sort of shows us what arrays look like in memory. So we've just talked about this. The array name itself, if we try to print that out, that will tell us the address where the array starts. So basically, with an array, you've got a chunk of memory and you know where it starts. All right, this is the starting address. There's some memory. You need to keep track of the size that it was, right? How many elements in it. And they're all next to each other. So C can very easily work out if it's got the starting address and you say, I want the one at index 3. Just using simple addition, it can work out, oh, well, it must be at address 36 if integers are 4 bytes, etc. It can just do a calculation and jump straight there. So random access is really easy. So sequential because they're all next to each other. When we store linked lists, if I wanted to store this same data, it might, and again, these are just made up addresses, it might look something more like this on the right-hand side. I know the starting address of the list, and here's my 13, but the next item isn't next to it in memory. It could be anywhere. And the next item after that could be anywhere. This is what we mean by it's not contiguous. And it's also hard, I mean, C can't work out from the starting address where the 10th element might be, because it could be anywhere. So how does this work? So for every piece of data that we're actually trying to store, we have to also store an address. And it's the address of the next piece of data. So it's a bit like a scavenger hunt. Has anyone done that where you go along and you get different clues? You've got to go to the, I don't know, the oak tree up in the backyard and get a clue. Then you've got to go to the, I don't know. I don't think I've actually done one myself. They sometimes have them at uni, right? Scavenger hunts. Anyway, we can do one now, right? In case you've never done one, here we go. So the list, we'll know where the beginning of the list is. This list variable that we somehow make in our program is going to know the list starts at address 28. We go to that address and we think, great, I've found the value 13. Now it's also got the address to tell us where to go next. I've got 13. Let's now go to address 80. When I go to address 80, what am I going to get? I get the value 17, and then the next value will tell me, okay, now go to address 60. I go to address 60, I get the value 42. It tells me, now go to address 48. I go to address 48, I get the value 5, and then it says null. That means there's nowhere else to go. You've reached the end of the list. You can stop. So this is how linked lists work. This is one we've already created. I'll show you how to create them. But we've basically just traversed our linked list. Traverse means start at the beginning and go to the end. And traversing a list is something very common, because if I want to print out all the elements, I would do this, but print everything on the way. If I wanted to count how many things are in there, I'd do this and count them on the way. If I wanted to search for something, I'd do this and check if any of them are the ones I'm looking for. Yep, I've got a question.
Yeah, so if you make a linked list, is this automatically generated, or is it like one linked list to another linked list?
I'll show you how to do it in a minute. But basically, yeah, I'll show you how to do it. So I'm just showing you, once you've got one, this is what it looks like and how you do it. But now we've got to work out, how do I create one of these things? Because we're responsible. There's no syntax in C that does this for us. We have to, like, using just array brackets or something, we've got to do this ourselves. Yep.
Do you have to assign like the chunks of memory to
Yes.
the list?
Yes. So we're going to do, people are asking awesome questions about how we make these things, and that's what I'm going to show you next. So I've talked about it's sequential. We can't just jump, like, there's nowhere to compute where element 4 is without going through the whole list and following all the different addresses. Now let's think about how we could write code to do this, which people are already thinking about, which is good. If I wanted to have a type in C that could store, in this case, an integer and an address, what type would that be? What? Yeah, a struct. A struct that has a member that, in this case, is an int, and a member that has a pointer, because a pointer can store an address. So each of these, each of these are structs of this type. And again, the name node is just a name that you can make up, or it could be something different. But everywhere you'll see, when you've got a linked list, we tend to call it node. So we're going to call these things nodes all the time. And it's always got some kind of data. It doesn't have to be int. It could be char, could be a struct, it could be an array, it could be lots of data. But what it's always got is some data in it, and then this thing here, this is what makes it a linked list, because it's got a pointer, or the address, of the next struct. And it's a pointer to the next struct of the same type. It can't just be some pointer to some random struct. They all have to link up together. They all have to be structs of the same type. Each one has the address of the next one, which has the address of the next one. So this is the struct we use. So this is a struct, this is a struct. They're all structs. Yeah, I saw a hand up over, yeah?
So just to understand, are these just structs within structs?
They're not structs within structs. They're structs that know where the next struct is. So I've got a struct, it has data in it, and it has the address of the next struct. So I'll just, they're not all inside each other. Okay, so let's keep going and write some code, and I'll step you through it. And what's what type of variable do we make that stores this list? This variable up here, if we want to create a linked list, is also just a pointer to one of these nodes. So in this case, our list really just has the value OX28 in it. That's where the start of the list is. That's where the first node is. Then this node has the value 13 and OX80 because OX80 is the address of the next struct. Okay? Yep.
How does the computer know after checking OX28 to go to OX32 where the address is? Or am I?
The question is, if we know to go to address 28, what we've got at that address is a whole struct. We've got a whole struct at that address. The first field will have the data in it. The second field will have the pointer in it. So it'll span a few addresses because it's a struct, but we know how to access the data member and then the next member. All right. So let's keep going because it might become clearer as we do it. If not, I'll go over it again. This is how we typically visualize these things. So I'm not always going to type up huge chunks of fake addresses in RAM, but we tend to draw it something like this, showing us the start. Now we sometimes call our list variables head to mean the beginning or the head of the list. We sometimes call the end of the list a tail. So you might see the words head and tail, first, last, beginning, end, list. We call these nodes, and yeah, they all have some kind of data, doesn't have to be int, and then a pointer to something of the same type. And when we draw it, we just draw these arrows to show, well, this one knows where the next one is, so it's linked together. All right, so that last example that I showed you, we could draw it up like this. I've called it head instead of list now, that's a bit confusing, but this is like our variable that's storing where the beginning of the list is. And in our example, it was 28. This first node has in its first member data. In its second member, it has a pointer to the next struct. The next struct, I've got fake addresses written up here. Let's say it's at address 80. It has an integer item or data, and it's got the address of the next struct, which, you know, in my example is 60, etc. The last one has null in it. Okay? So this is how we'll be visualizing them for now. Yep.
So the one byte can store the whole struct. Is that what's happening?
Oh, can you repeat that?
So is this one byte, like the 28 and the 80?
So this would be however the size of this. Whatever this struct is, the size of it. So we could try and work that out ourselves, but it's going to be big enough to store an integer and a pointer to an integer. Yep, so it's going to be, you know, maybe 16 bytes or something. We don't have to know exactly in this course. Yeah?
Are all of these structs like malloc?
Very good question. Are all of these structs mallocked? Yeah, we tend to malloc them because we want to be able to malloc these things as needed. We don't know how many of them we're going to need in advance. And also we want functions to be able to malloc them for us and return them. But yeah, we don't know how many of these structs we're going to need. As we want to add stuff to the list, we just do a malloc, we set the data inside, and we just play around with these addresses so they're linked up to the rest of the list in some way. So let's have a look at how we actually do it. So yeah, when we've got something like this, this is how we typically initialize our linked list. This is an empty linked list. It has no data in it yet. Okay, and I might draw it like that. So we've done our first linked list. It's an empty one. How do we put a node in it? Let's make a linked list with just one node for now. Somebody already asked, yeah, what do we use malloc? Yes. So we malloc a struct, we set the data, and we set the pointer to connect it to the rest of the list, and that's it. So in this case, we've got a list with nothing in it yet. This is here to remind you of what the struct type looks like, what struct node looks like. And we've got our empty list. Is everyone happy up to now? It's a list. Where's the beginning of the list? Null. There is no list yet, really. There's no data in the list. So I'm going to just malloc one chunk of memory, because I'm just going to make, in this example, I'm trying to do it the simplest way possible. I'm doing a malloc. When we do a malloc, it's going to create some chunk of memory on the heap, and that chunk of memory is going to have an address. And that address gets passed back and stored in our variable. So this chunk of memory, somewhere on the heap at address 88, I've decided, and we store that in our variable that we've called head. So now head is actually not null anymore. It was null. It was null here, but now we've done our malloc. It's got the address of this first node. Is everyone happy with that? So we've already got one node, but it's got garbage in it right now. We haven't put any data in there. So now I could say head, like I've got a pointer to this node, which we've called head. I can set the data inside to be 21, all right? But so far there's nothing in this other member here, right? We haven't put anything in this next member in our struct. If this is the only node in our list, what are we going to put in this field here? Yeah, we put null, because null means there's nothing after this node. Sometimes we just initialize things to null to start with and then set them to something meaningful later. But here, if this is our only node, there's nothing after this, that node will have null as the next address. So now we've actually got a linked list with one piece of data in it, okay, that we've malloced. Are there any questions about that? So I've got a chunk of memory that I've malloced, and I've got a pointer to it, and I've set some of the fields in that chunk of memory. And it's basically a list of size 1. All right. Yep.
Why do you have to knowledge just to set it equal to a number?
We want to malloc it because we want a chunk of memory. Oh.
No. Why do we set it equal to null and then we have to set it equal to a number?
All right, so the question is, why have we set head to null and then we've set it to something else? Typically, we'll start off with an empty list, and as we need something, we'll do a malloc and add it to the list. So at the beginning, when there's nothing in the list, it's equal to null. There's no data for it to kind of point to. Then in our program at some point, we'll need to store something. Then we do our malloc.
The node's not by default? Or
The node's not by default. Every time we want to store something, we do a malloc to store that new piece of data, and then we add it to the list. So it starts empty. We start mallocing and adding things as we go. It's not like an array where we try and get a big chunk of memory to start with. We just do it one by one. Okay? Yep.
Like there are 2 or more elements, like structs in the same place. How are we going to store so many names of the struct?
Okay, we've got a few good questions here. One of the questions was, if we've got so many structs, how are we going to store all these different variable names? Is that going to be kind of like having just 1,000 different variables? We don't actually end up storing all of the... Each struct won't have its own variable name. When you do a malloc, it doesn't necessarily get its own variable name unless you assign it to a variable. So just wait and we'll see what happens as we add more. Okay. So we've got our linked list of size 1 and we're going to create another node. And then we can decide, do we want to put it at the end or the beginning? But anyway, to create the next node, we're going to do a malloc. So I'm going to add it to the end. We're going to do a malloc. And we know to do a malloc, we'll have a break in a minute after we've added this second node. To do a malloc, we do the malloc just the same as before. Just concentrate for 5 more minutes. So we've got a new variable, one new variable called new node. And this, we're going to do a malloc. We're going to store the address of that new node in this variable called new node. But right now, and I'm setting the data to 99 and null. So right now I've got 2 nodes, but this new node is not connected to the list, right? It's not connected, it's just a node on its own so far. But that's the first step. Now I've got to connect it to the list. Now, if this is my list, and I want to connect it to the end of the list, basically I want this to point here, right? If I'm adding it to the end. So what value do I want in here instead of null in this example? Yeah, so I've heard like, yeah, OX84, which is basically new node. So new node has the address of this new node. We want the address of this new node in here because that new node is the next node in the list. So this is linking it all together. So I've made my new node. I'll get rid of this now. I've made my new node. It's not connected. But now I'm going to say, oh yeah, and what is this field? This field here is called, well, this whole thing here is called head. Oops. I'm going the wrong way, I think. Hang on. Pretend you didn't see any of that. So head is a pointer to a struct. To access the data field, we'd say, well, head.arrow data or new node arrow data. To access this field, we say head arrow next, right? This is head arrow data, head arrow next. So we're setting head arrow next. So now, head arrow next, which is this field here, has the same address in it that new node has. This has the effect of linking this up, and now this first node is connecting to this last node or second node, new node. All right, does that make sense? Now, is there anything else to do in this situation? Now our list goes, well, the starting node is at address 88. We get a 21, and then it says go to the next node. Well, it doesn't say go there. It says the next node's at address 84. When we go there, we see 99, null, we're at the end. We've got 2 nodes. Any questions before I move on, or before we have a break? Okay. So yeah, let's have a quick 5-minute break. Or let's come back at about 5 past. 5 past. I'll leave that here for people to look at. So, everyone, we're going to get started again. So we malloced a new node. We connected it to the end of the list. Let's just see how we could have connected it to the beginning of the list. And then we'll go on to make lists with more than just 2 nodes in it, okay? So, so imagine we've gone back to our original list that has 1 thing in it. Now imagine I've done another malloc. I've done a malloc. I've got some new node, and the address is 84 of this new node. I've put data 99 in there. What do I want to put in new node next to connect it to the beginning of this list? So this is the beginning of the list. Yeah, so I heard 2 answers, both of which are right. We basically want this to be connected to here, and that's 0x88. What variable has that in it? Or head would. So we're basically saying, I want this new node to be connected to the head of the list. I want the next thing to be whatever's already in the list. That's what we put there. But then what's wrong with our list if I do that? Where does the head of the list think it is? Yeah, so where does it need to be? What's now the first node in the list? Yeah, so now the head of our list shouldn't be pointing here anymore. This is now the head of the list, right? Because we've inserted something at the beginning. So this variable here always has to keep track of what the first node in the list is. So we don't want it outdated thinking, oh, here's the beginning of the list and I've added all these nodes in front of it. Then if you go and try and use it, you'll have lost all your data. So yeah, we have to do these 2 steps. We say new node next equals head, and that puts this connection in here, and this, is connected to here. But yeah, we've got to make sure the head variable is updated so it's connected or pointing to the correct first node. So this new node that we made is now the head of the list. Head just means the first element in the list. All right? So when we're doing this stuff, it's always a matter of mallocing things and then just making sure the right addresses are in the right places, the right pointers are set up. Okay. Any questions about that? So now our list, we go to address 84. We know we've got the value 99. We know that we now go to address 88. We get the value 21. Then it says null, so there's nowhere else to go. And these are just 2 structs and 2 variables. Any questions before we go on? Okay. So what we're going to do is we're going to code some of this stuff up, but we want to actually create 3 nodes. Ooh. So let's see how we go with that. And then we're going to print them. Just the 3 nodes. Oh, why did I do that? Okay, so we're going to start with an empty list. Struct node head equals null. That's our list so far, but we're going to create a node, and look, we should do a function to do this, but for now I'm just going to write the raw code. We can put it in a function later. So let's, to be consistent with what we drew before, I'll call it new node equals malloc size of struct node. And look, we are meant to check whether that new node returned null. I'm just going to leave it out now because I just don't want extra code here. So at this point, I've got I've got a variable called head that's equal to null. I've got a variable called new node, and I've done a malloc. So when I've done my malloc, I've ended up with a chunk of memory at some address, right? And I'm storing that address in new node. Malloc returns this address for me. Whoops, I can't write. So it's kind of like, you know, this is pointing to this struct, right? So this is all we've got so far. Now I put some data in here. So I'm going to say new node, oops, data equals 3, whatever. So I've got a 3 here. Now at this stage, there's no other data, and I would say new node next equals null. So now I've got a list with one node. Okay, I'm going to add them at the beginning. But now, where is our list? Our list still thinks it's null. We've got to make sure we update our list or head variable. So we want to say head equals new node, right? So now head, instead of having null in it, oops, has the address OX E0. So yeah, head's also pointing here. Okay, we want to make another node. So I'm going to, now I don't want to keep making a new variable for every single node, right? I'm just going to reuse my variable new node and say new node equals malloc size of struct node again. Okay, so now new node isn't pointing to this, but that's okay because the head is. So new node, let me get rid of that. I'm creating a new node for new node to point to. So let's imagine that this address is OX, it doesn't really matter, F4. Right, so we've got a new node that I've malloced. So I've malloced a chunk of memory. I've got the address of that in my new node variable. Now I can set its data. I can say new node data equals 9, whatever. But now I've got to say new node next equals what? So I'm adding it to the beginning. I want this to point to here. This is where head's pointing. I want it to actually have the value address E0, right? Which is this next node, and that address is stored in head. Okay. All right, so now I've connected it up like this. Yeah, but now my head is still outdated. It's pointing to the wrong node now. I've got to say head equals new node. Now I can do this again and again and again and again and again and keep adding nodes to the beginning. So I'm going to get rid of this. Okay, and you notice that there is no variable, there's no separate variable for that last node anymore. There's no extra variable pointing to that last node. It's connected via the list now. So usually we just keep a pointer to the beginning of the list, and we've got this new node thing, which is sort of like a temporary variable. We just creating a new node, we temporarily point it to that, and then the rest is just all connected. Now, if I make one more node, because I think I said I was going to make 3, we pretty much do the same thing. And when you're copying and pasting like this, you know that really you should have a function, but we'll leave it like this for now. I'm going to make the data in the new node. Let's just make it 7. So now I'm creating another node. That address might be, you know, something else, E8. I'm putting the value 7 in there, and I'm saying new node next equals head. Well, the value in head is OXF4. So now this new node, oops, I forgot to put the addresses in here. So now this new node is pointing to the head. So I did my malloc. So new node is pointing to this new malloc node. I put the 7 inside it, and then I connected it to the head of the list. It's pointing to the head of the list. In other words, this next field has this address in it. And now I've also got to say, well, actually, this is no longer the head of the list. This is. So I've got to update the head of my list appropriately. Oops. And in this case, I'm setting it to new node because that new node is now the first node in the list. Okay. And I can keep doing that and doing that and doing that. I won't manually because it's hurting my brain trying to draw it. Yep.
Can we make like a new function and use a for loop and like keep this running?
Yeah, so that was a really good suggestion. Can we have a for loop or a while loop doing this? Yes, yes. If you know what the values are though, you'd have to know what the values are, but yeah, you could have a loop saying to the user, what value would you like to enter? And they can tell you 7, and you just go ahead and do this and add it to the list. Or you could have, I mean, I'll show you later, we can just hard code a list with 0, 1, 2, 3, 4 or something. We'll do that, yeah. But yeah, and we put this because you can see how repetitive this is. This does really well in a function, that kind of code. But that's the principle. Now, if we're still doing things just in sort of bad, dodgy ways, how could I print out these nodes? Again, we want to learn how to do this with a loop and with a function. But just say we're desperate right now to print out these 3 nodes. What would we do? Well, and by print, we want to print out the data that we're trying to store. So the data we're trying to store are just the integers. The addresses that we're storing are just stuff to make the linked list work. So I want to print out the data in the first node. I would say head, arrow, data. And that's going to print out, because head points to this first node, I go to the data, and I get 7. How do I get to the second node in the list? Yeah, so head takes me, head is the address of the first node. Head next, so the next field in here contains a pointer to the second node. So I could do head next data. Print that out. I could then print out, what do you think the next one is? Yeah, I could print out head next next. And if I had a list with 1,000 nodes in it, I could say print head next, next, next. Anyway, we don't want to do that. We want to learn how to do it with a loop. But this should work, right? We'll see. Let me get rid of this for a minute. Was that what we had in the list? Yes, 793. And you'll notice if we're continually adding to the beginning of the list, you know, the first one we add ends up at the end, right? Because we're adding them at the beginning. So we end up with the last one we added at the beginning in this case, because we kept adding them to the beginning. All right. Now, do we think we've got any memory leaks? Yeah, we do. So if I ran this, yeah, it starts telling us we've done mallocs without freeze. For now, I'm going to leave that. We'll deal with free in another lecture, just because I don't want to go through that now. Okay. So how can we move the code to create a new node into a function? And then, as somebody suggested, I can't see you now, we could use a loop to keep adding to the head of the list like we've just done, okay? We're going to try that. Then we're going to look at how we could print out a whole list, even if it had thousands of nodes, instead of just keeping on saying next, 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 and typing that in. If we have time, we'll look at adding more things to the end of the list, because we're going to do adding it to the beginning. Free nodes we'll do later. Okay, so we're going to write this create node function. So let's write it from scratch. We're trying to create a node. So we're still going to have our malloc. And we're going to do it like that. And now that it's in a function, I'm going to be a bit more careful, and I'm going to error check. Because now I only have to do my error checking in one spot rather than all that hard coding I did. So if it returns null, well, then it was not able to give you memory for your node. So if you've made 10 million nodes already and you're trying to make 10,000,001 nodes, maybe malloc's going to fail. So you might want to print out a message. I don't know what you might want to do. I'm just going to return null in this situation as well. Probably not going to happen in our small little example today. Because if it's null, I can't then go and set the data inside it, right? So now all I'm doing is I'm copying my data into this new node. And in this function, I'm passing in the address of the next one. So I'm not even thinking about what the next address is. It's just being passed in by whoever's using this function is saying, put this address in this node, put this int in the node, put this address in the node. I'm just blindly copying it in. Next equals next. Then I return it. So this is just doing the mallocing and setting of the fields, just to save me doing that all the time. So now, if I want to make a node, let's just make one node for now. I could just say create node, pass in some value like this, and now I've got a node. Is everyone happy with that? I've basically just moved all of that stuff I was hard coding before into a function. Does anyone have any questions about this function? It's pretty much what we just did before. We're doing, a malloc gets a chunk of memory. We get the address of that memory. We're setting the data inside it to be, I can't remember what I've just said, whatever it is, and null. That's how we're going to be using it. And we're returning a pointer to that chunk of memory. So now in our program, when we want to create a new node, we just call that function. We pass in the data we want it to have, and we tell it where we want it to connect to. We tell it what node is after this node. So I can do that. So what I'm going to do now is I'm just going to use this repeatedly in a loop, and I'm going to make nodes from 0 up to 9. So I'm going to say new node equals create node. I'm just going to pass in I. So the first node we create will be 0, and the next node that we create will be 1, etc. But how do I want to connect it up? So now we have to think a little bit of how we're using this. So in this example, I want to use it again to connect nodes to the beginning of my list. So my list head right now is equal to null. And this new node, the first node I make, is going to have a 0 in it, and I want it to connect to what's already in my list so far. What's already in my list so far is nothing. So I'm just going to say, but it doesn't matter, I'm just going to pass in head. So if there was anything in the list, I'd be saying I want this new node to go before anything else in the list. Right now we know the first time we do this, the head of the list is null. This first node will be connected to null. So this is our new node. Maybe I'll continue with these addresses, these fake addresses. Now, right now, oh yeah, and I should write this in here like I've been doing. Is equal to what? So yeah, now what we want to do, that's correct. I've got new node pointing to this new node, and I've connected this node to the rest of the list, which was easy because right now there's nothing in it anyway. But yeah, now head still has a value null in it. So now I need to update that. So head is actually now equal to new node. So now head has the address of this new node in it and is pointing to this new node. Okay, now I'm just doing this again and again and again and again and again. I make another new node, starts getting messy. Especially when I use the wrong color. I make another new node. Next time around the loop, just try to be quiet just so I don't get more disturbed myself. Next time through the loop, this is the tough one, I'm putting the data 1 in there. But now, again, I'm saying the next one is going to be head. What's the head of this list? Well, it's not null anymore. It's 0 up. The value in it is 0. The value in it is null. But head contains this address 84, and that's what we need here. So we're saying connect it to the head. The head is at address 84. So this new node is now connected to what's currently in the list. Okay, and now we say, actually, this is not the beginning of the list anymore. The beginning of our list is this new node, which has address 80. Now we do this again. We create a new node. That new node will have its own address, whatever it is. And this time we know, because we're using a loop, we'll be passing in the value 2. And we want it to connect to whatever, oh, I didn't draw this link in, whatever the head of the list is. So we say equals head. So now this will have the value or address 80 in it. So now it's connected to here. And again, we've got to say, well, actually, this is no longer the head of the list. this is. So you can see we don't end up with a variable for every single node in the list. We'll keep going and doing this repetitively again and again and again, mallocing and setting the next to be what is already in the list. Okay? Then saying, well, actually now this is the beginning of the list. Do you have a question? Yeah?
Why do you not need the ampersand? Because we need head to equal to the address, right?
Well, if I do ampersand on head, I will get the address of where I will get the address where head or new node live. So if I just say new node, I get the address that's stored in it. If I say address new node, I find out where new node is stored in memory, which is not what I want to do. So I've already got a pointer. I've already got an address in this new node variable, and that's what I'm looking for here. Does that make sense?
Yes.
If I put ampersand new node, I'm finding out where new node is stored, and we don't really care about that in this situation. We care about where these actual malloc nodes are. Yep.
Am I right in saying essentially like working back to front because we have like our head being like the front, we keep adding stuff to the.
Yeah. So.
Can we work in reverse?
So yeah, that's a good question. We're working back to front by adding something at the head of the list. We end up with a list in reverse order. The reason I'm doing it like this, which is very confusing to do something in reverse order, is because we've got a pointer to the beginning of the list. If I want to add something at the end of the list, and if I've got a traditional linked list that just has a pointer to the beginning, I've then got to find the end of that list and then add the node on. And we're going to do that maybe not today, maybe next lecture, just depending on how we go for time. So that's a little bit more work. If we've just got the pointer to the beginning, we'd have to go along, this is the last node, let's add it on there with a traditional linked list framework. All right. Let's move on. We want to start being able to print these things out without having to do what we did last time, which was hard code a lot of nexts. So I've done the create node. I've done that. Okay. So how could I print data from the first node? Well, we saw that already. I can just do printf %d because that's the kind of data we're storing. %d head arrow data. And that would print out the 13. How do I print the next one without hard coding next? Well, typically we create another pointer that goes along one by one through the list, and we move that pointer along. Now we don't have to call it, I'm going the wrong way, oh my goodness. I'm going backwards like my list examples. Okay. So yeah, this is typically what we do. We set a pointer to the beginning of the list. Now it doesn't have to be called current, but we often do call it current or car because we're lazy. Well, most people typing don't want to type out the whole word current. I set it to the beginning, so I make it equal to head. It's going to store the same address head is, which is the first node in the list. And then I'm always printing the one at the current. I go current arrow data and I print it out. But then I want to move current along to the next node. How do I do that? Well, yeah, I ask current. The next node is current next. So if I go to current and go to the data field, I get 13. If I go to current and go to the next field, I get this address 80. This address 80 is basically the address of the next node. So I say actually current equals current next, right? And next time I do it, current will equal, this is current next is 60, current will be equal to 60, it moves it along. I just keep saying current equals current next. Each time I print it out the value inside it. how do I know when to stop? Because I want to put this in a loop. How do I know when to stop? Yeah, so when I get to the end, current next will be equal to null. I still want to print out my data though. So I can even just go past it until current is equal to null in this case, and then I stop. If current's null, there's no more data in the list. While current's not null, I'm pointing to some node in this list, and I want to print it. Yep.
Once this list finished, they're going to print 13, 17, 42, 5, or it's the other way around?
Well, if I do it like this, if this is my list and I start at the beginning and I print it, yeah, I'll get 13, then 17, then 42, then 5. Yeah. So let's do this. I'm going to create a function called print list. I'm going to pass in my list, and it's going to print it for me. Let's try it. So, like I showed you before, we're going to create some kind of temporary variable called current, and we're going to make it equal to the head. Now, when I draw these things, I'll probably won't draw all the details on all the time. And I'll probably draw it pretty badly. Right. So we've got something like this. We've got a list with some data in there. I'm going to make a pointer called current, which is basically just pointing to where head's pointing, which is this first node. Okay. Now, I'm going to have a loop, and I'm going to say while current, actually let's just call it car. While car is not equal to null, then I want to print out this current node, like print just the integer that I'm storing in it. To do that, I've got a pointer to this node called car. To get the data that's inside it, I say arrow data. So I'm printing out the current data. Now, if I just did it like this, I would have an infinite loop printing out the value 9, right? Current's always at the first node. I'd just be printing 9, 9, 9 forever. I want to move current along. I want to get that next address out of my current node and then move along to point to that next address. So I say car equals car arrow next. So this is going to be, remember when we learnt arrays and we first learnt to have our while loop that had I is less than the size, I plus plus, you know, and at the beginning int I equals 0 or something like that. This is going to be a bit like that. You're going to use this again and again and again for different types of things. Whenever you want to go through your list, you'll have some kind of pointer to the beginning that you can move along one by one in a loop like this. Okay, so let's try it. Oops. Let me run it again. Wow. We got our list printed out. I don't need this at the end. Actually, let's do a space. Look, we can even do lots of things with this. Beautiful. But remember, it's backwards because when we created the list, we made the list in this order. The list has 9, 8, 7, 6, 5, 4, whatever. Did someone have a question? Oh, yep.
Where's the numbers coming from?
We've already got a list. So we've already created the list up here. We've created this list, and we pass in a pointer to the head of this list. So we've already got a list made, and we're passing in. This is the address of the first node in the list, and then our print list goes, okay, and it does like the scavenger hunt. It prints the first one, and then it finds the address of the next one and moves to that one. Then it prints that one, finds the address, and when it gets to null, it knows, well, there's nothing more in the list. Yeah. Yeah?
Generally, like creating the list, that part, should that be in function?
Yeah, so typically we might have a so the question was, should this list creation be in a function? Yeah, typically we want functions for this. So we might have a function, I don't know, add to front or add to head or something. We're going to see maybe today a function to add to the end of the list or add to the tail of the list. Yeah, so yeah, nicer if you have all these. And then in your main, all you do is call a whole heap of functions. Yep.
Where have we hard-coded the 0 to 9 from?
I hard-coded it here. So in this loop, I was 0, I created a node with the value 0 in it. Then I created a node with the value 1 in it, 2 in it, 3, up to 9.
For loop is basically codes the data part.
Well, in this example, yeah, I just got a for loop to code the data part in, and I just created nodes with that data and I added it to the list. Otherwise, you might be reading in data from a user or a file, you know, somewhere else. But just for this example that's not doing anything, I just, yeah. Just so I don't have to literally type them all in. Yep.
To add to the tail, would you make another point that points to the tail? You know, use the same method to add to the tail.
So somebody just asked a question, if I want to add to the tail, do I make a pointer to point to the tail and then add?
If you don't do that, you have to keep traversing.
Yeah. So when we want to add to the tail, we somehow have to have a pointer to the tail, right? We have to somehow know where the last node in the list is, have a pointer to it, and then connect our new node. Now, whether we have a loop to find that last node each time, or whether we store another variable to always keep track of the last node in the list, that's another question. So the way we're doing it in this course, the standard linked list just has a pointer to the first node. Anytime you want to find the last node, you have to do a loop to do it. Then you'll see people trying to make more efficient things like, I'm going to store a pointer to the last node too. And that can make sense, that can make things easier, but you've got to then make sure you update it, right? And yeah, you can't have a pointer to every single node. So yeah, at some point, you know, but yeah, that's a very good question, and that's one kind of optimization you'll see. All right, we've got time to go through this even if we don't have time to code it. So is everyone ready to pay attention? Or do we want to do a Kahoot instead? All right, we can do adding to the tail next time because you've already done a lot. Yep, let's do the Kahoot. Hang on, where's my web browser? All right, in the interest of not overloading you too much. Okay, Kahoot time. Everyone join the Kahoot. I'll give you a few minutes to join. It's on pointers, which are, you know, important to know for linked lists. Are there still people in the room trying to join? Okay, I can see it rising a bit. Oh, wait, another minute. All right. Okay, let's do it. Let's do it. Hopefully there are no wrong answers, but if there are, the first person who finds it, I don't know, just gets a chocolate. There's no right answer to this one. Moderately, very familiar. Okay, there's still some not at alls. That's normal. Yay. Yeah, so a local variable, just a normal variable on the stack. Agile emu. Do you remember what stack frame means? Okay, so a stack frame, every time, when we run a function, a stack frame gets pushed onto the stack for the main. So when we're running the main function, there'd be a chunk of memory. Oh, that's not a good color. There'd be a chunk of memory for the main, as variables. Then main is running the function foo. So we'd have another stack frame for foo. Then foo is running the bar function. So at this point, we've got 3 stack frames because we've got a function that's running a function that's running a function, calling a function. So that's 3 stack frames. Yeah?
So, wait, is a stack frame just like a function within a function within a function?
A stack frame, a stack frame is just a chunk of memory set aside for a function. So if a function's running, it's got its own little chunk of memory that it can store stuff in. When that function finishes, that gets taken off the stack and it can be used for something else. So once this function finishes, this gets popped off the stack and it can be used for something else. We might call another function. Once foo finishes, this gets popped off the stack. Once the main function finishes, this gets popped off the stack. And then, of course, you know, our program's going to finish then anyway. So yeah, at that point, when we've got 3 functions that are all running, or, you know, it'll be 3. So there's another one here, so see how you go with this one. Oops, I've got my thing in the way. Yep. Two. Very good. So remember, we have main. We have a stack frame for main that has main's variables and data in here. Main calls the function foo. We end up with a chunk of memory for foo. Foo calls the function bar, and that has some data. But by the time we get to whatever line 13, that function's finished. Bar's finished. So we've got two stack frames. Bar's stack frame would have been popped off the stack. And this is what's automatically happening for us to make our life easier. But then sometimes is annoying, and that's why we use malloc. Actually, this is a little bit badly worded, to be honest. Okay, so yeah, honestly, the wording was a bit dodgy, but it's saying if we pass in this array, a function can modify it. If I pass in an integer, it's a copy, the function won't be able to modify that original value. If I pass in the point, it's a copy, the function won't be able to modify that original value. But with an array, it can, because we actually send in the address. Okay. Yay, most people got this right. Ampersand gives us the address. Well done. Okay. Got a few more. Oh, we're running out of time. Yeah, so this is declaring a pointer variable called num2. Okay, it's not initializing anything. All right, sorry, charging through it. Ooh, most people got this right. We had num_p is a pointer to num. If I do star num_p, I get the 5.2, and then I add 2 to it. Okay. Couple more. Sorry if you've got to go, that's perfectly fine. Yay. So if we've got a pointer to a struct, we use arrow to initialize the members. Again, I'm going to quickly get on to the next question. Oh, I'll just quickly go over this. If I've got a pointer, if I do this, this pointer has the address of the array, so it's pointing to the first element in it. If I do star pointer and it's pointing to the element, it'll give me that element in there. So I can, when I just use the name of the array, it gives me the address of that chunk of memory for the array. I've now got an address in a pointer variable. I can dereference it and get the value. So the answer's 1. All right, I think we've got one more to go. Okay, last one. Okay, this one's command line arguments. Okay, I don't have time to recap what they are because we're running out of time. If you're the winner, there's chocolates. Go and see Brianna. Prairie rabbit. Prairie puffin. And melodic sphinx. And runners up, you can get chocolate too.